and introduce our speaker today. So our speaker will be Dr. Allison Goodwell at the University of Colorado, Denver. We will be discussing a framework for causal discovery in non-intervenable systems. So thank you, Allison, for being our speaker today, and the floor is all yours.
All right, thanks, Layla. Thanks everyone for joining. Sorry if this is not super organized. I read this paper really well a couple weeks ago and I made this presentation and I thought I would come back to it in the last couple days. But as we were discussing, we have a toddler at home instead, and that's what I've been doing. So hopefully this will go smoothly, but we'll see what it looks like. So the paper for this week that some of us read is called A Framework for Causal Discovery in Non-intervenable Systems. And it's a pretty recent paper, basically from this year, and it's on the archive. Whoops. All right, so the kind of the just to introduce the idea of non-intervenable systems. It's kind of in contrast with the concept of Pearl causality, which is based on a causal network or defining a causal structure based on interventions in the system. So you remove some variable and see what happens, or you do a clinical trial essentially, or do something that you could do in a model. However, there's a lot of cases in the natural world where we either can't do this type of intervention, like it's physically impossible to remove some variable completely from the system, like you can't remove temperature or something from a system, it's always there. And one thing that this paper brings up that I thought was just a little bit different than I had previously thought about this before was that in some systems, even if we could do an intervention, or we shade a plant, or we kind of create a dam or something and then intervene, that manipulation of forcing might basically change the entire structure of the network in some complex way due to all these feedbacks that might exist in these types of complex systems, and basically push the states off of their attractors completely to the point that we don't know what we're even looking at anymore. So either way, whether we can't do it or we could make some intervention, we're not sure what the implications of that intervention are. So we're basically kind of living in the non-interventional world of observations, where all we have are observations of a system. So that's where Granger causality comes in, and a common information theory measure that's often associated with Granger causality is transfer entropy. In Granger causality, we say that a source is a driver, or a source is a source of information to a target if it reduces the uncertainty of the driver. And that is beyond the uncertainty that the target itself can reduce given the knowledge of its own history. So that's where transfer entropy comes in. Transfer entropy is a conditional mutual information measure that gets you exactly that. So it's the information that a source provides to a target beyond the information that the target can already attain for itself, given the knowledge of its own history. So that's kind of where this paper starts, is, this is the type of causality that we're looking at, is essentially Granger causality, which is just based on observations. And then it kind of goes on to talk about how many causal detection methods rely on graphical representations of the network, which are kind of like the top, this top ABCDE figure that I have here, where what we're considering are these kind of pairwise links between these variables. I also added this causal history graph in the middle as another example that is showing more specifically, and here there's 4 nodes that are different colors, and we're kind of marching through time, and so the arrows are showing a more diverse set of time dependencies than you would just be able to see with this network up top, but it's still essentially illustrating a pairwise type of interaction, so a cause from one variable to another. And what this paper is interested in, and it's kind of something that I've been interested in general, is interactions from multiple sources to a target that can't be directly drawn as pairwise links. And that's what this bottom plot is showing. So it's a pretty simple 2-source, 1-target system where X is going to be our target throughout all of this. And Y and Z might provide X some information individually, but there's also this sort of joint awkward looking interaction, which I'll talk about next. So basically it's types of causal networks where you might not be able to draw the network directly as pairwise links. So they talk about this in the context of polyatic versus dyadic interactions, which is the same thing as saying joint versus pairwise types of interactions. And the example that they give is, the toy example that they give is one that I hadn't seen before, but it is very similar to the binary XOR problem. If anyone's familiar with that one, I know many of us are. So this is an equation where Y and Z are obviously drivers of X, and there's no time lag or anything here. And Y and Z are independent with a probability of being 1 or -1 of 0.5. So you can see that given just one of Y or Z, that tells you nothing, and this is a noise term. So given just one of Y and Z, so say we know that Y equals 1, that actually doesn't provide us any information on X, because there's still a 50-50 chance.
Why didn't you go that way?
There's still a 50-50 chance that the other variable is 1 or -1. So there appears to be no information provided by Y and Z to X. Which we know just by looking at this that's not really correct. And in fact, when we consider the knowledge of both Y and Z, we have, beyond this noise term, we can just ignore this noise term for the moment. If we know both Y and Z, we are absolutely certain of X. So obviously somehow Y and Z are providing information together or jointly that they don't provide individually. And one way to address this aspect of joint or polyatic types of interactions is through something called partial information decomposition, which I'm going to go into a little bit, and then we'll kind of jump back to it in the context of this paper specifically. So in partial information decomposition, we are essentially decomposing the total information from, let's just say, 2 sources to 1 target. So Y and Z are the sources and X is the target. And we're decomposing into these four types of information. And we have unique information that comes from one of the sources individually. We have synergistic information, which is the joint information that's kind of exemplified in that previous example, where you need both drivers to get that information about the target. And finally, we have redundant information, which is overlapping information that maybe X I'm going to say usually X is a source. So Y and Z are the sources, and that's information that they provide in an overlapping way. So we could know one or the other, and they both provide the same information. And the nice thing about partial information decomposition is that we can also write all of these other information theory terms in terms of those 4 unique and redundant and synergistic types of information. So for example, mutual information here is a unique component from that source and a redundant component, which is an overlap with the other source. Similarly, conditional information here is a unique plus a synergistic component. So it's the unique information from that source, but instead of the redundancy, it's actually incorporating that joint type of knowledge that comes from conditioning on the other source. And then finally, interaction information is pretty important to this paper, and it's a redundant minus a synergistic component. So this interaction information, which I haven't popped this in here because I didn't get the chance, but if you imagine the entropy Venn diagram where you have the interaction information is that kind of very middle part. And it turns out to be the difference between redundancy and synergy, which is kind of a good explanation for why that interaction component can be either positive or negative, which can easily trip you up. So all this is nice, but however, as some of us know, information theory doesn't provide a way to do this directly. So there's essentially what we have here is 3 equations and 4 unknowns for these components. So we need another equation. And this paper goes with the idea that, we can't do information composition, but check out our papers. Just kidding, I'm not going to talk about that. So we're kind of going on the assumption that we're not going to actually do this information decomposition. And they make a couple of points about why not. First of all, it's kind of up to interpretation on what those components are. And that Williams and Beer paper that I was referencing before, for example, they have a method to compute redundancy. So there's been different proposed ways to actually do this information decomposition. But these authors kind of put up the idea that it's not clear if uniqueness can really be well defined in the first place. They argue that unique information should mean when Z is not present, and they kind of bring that up as if it should be kind of an interventional type of system where you can actually take out Z or tweak it. Whereas we're usually, all we can do is condition on Z, we can't actually remove it from the system. And in general, there's several existing methods to estimate these information decomposition components, and all of them are more or less flawed and subject to different interpretations about what is redundancy and what is uniqueness. So basically, this paper comes at defining causal interactions in a different way that doesn't directly apply PID. However, let's just take another
Allison,
moment. Oh yeah,
sorry,
go ahead.
Can I ask a question? If you could just go back.
Oh yeah.
I'm just trying to understand. So whenever I see conditioned on something, I tend to read that as given knowledge of, right? So this is a very different interpretation. Given knowledge of is saying given knowledge of and that it's not a present, as opposed to the classical interpretation, which is given knowledge of and I know what the value is, right?
Yeah. Yeah, I feel like they have a higher standard for what is uniqueness, and it's not only just knowing it. It's they're saying that it should be literally you remove a variable out of the system, and saying that we can't do that because we're in a non-intervenable system.
Okay.
At least I think I don't know. They could have meant something different. There's a couple pieces in here that I didn't fully grasp, I think. Yeah, so partial information decomposition, back to, just assuming that, what if we could do this? This is generally how we're looking at it. So here's just a couple visualizations before I go into a higher dimensional mode here. This circle, the whole area of the circle is the total information that 2 sources provide to one target. And these brackets are, this is straight from the Williams and Beer non-negative decomposition of mutual information paper. These brackets indicate, basically if numbers are together, that means synergistic, and the separate brackets indicate redundancy. So this outer is the synergy. This number alone is just the unique information from the first source. And this overlap here is the redundant information from both sources. And here is another way to look at it, and they call this the redundancy lattice, or someone has called this the redundancy lattice. And basically it's showing the same components. It's just saying, here in the middle we have uniqueness, and then jointly, so when those unique sources come together, they can either provide synergistic information or redundant information. And all of these dots or all of these components in here adds up to the total mutual information. And what that looks like for a 3-source system is it just expands the number of combinations. So once you consider more than 2 sources, the complicated thing about partial information decomposition is you don't just have uniqueness, redundancy, and synergy anymore. You have combinations of those different information types. So for example, up here we have what I would say is pure synergy. So it's information that all 3 of the sources provide only synergistically. So you have to know all 3 of them together. And on the bottom here, we have pure redundancy. So it's information that all 3 have in common with each other. And in the middle, that's the same thing for uniqueness. However, there's some weird combinations that take me a minute to like think about what they are. But just to give you a couple of examples, down here we have 1 and 2. So sources 1 and 2 provide unique information from 3, but they're redundant with each other. Up here, we have a case where source 3 provides information redundantly with the synergistic information that 1 and 2 provide together. And up here we have 1 and 3 and 2 and 3 provide synergistic information, but that is redundant. So those pieces of information are redundant with each other. Oops. And that's kind of where it gets complicated, is that we have all of these possible ways in which multiple sources can interact. And we don't just have only synergy and redundancy and uniqueness. So that's where I think this paper really, Uwe, do you have a question?
Yes. Is there any way to estimate in advance or with some rough estimates which of these components are maybe negligible and others you should focus on? You know, is there a targeted way of weeding out from that the non-important stuff?
Yeah, I think I think that this paper kind of gets at that, and I'll show a little bit of that later, because what this paper is doing is essentially it's kind of lumping, because like different combinations of these are computable. So like an information theory measure that we can compute is embedded within this thing. So you don't know an individual piece, but you can get combinations of them. And then if that combination was really small relative to another one, then that's a way that you could kind of say like, okay, there's dominant, you know, this set of types of interactions are more dominant for a system. Because this is the area where PID really not breaks down, but it becomes incomputable. So, you know, we think that we have ways we can handle this, you know, like I would argue that we can compute these 4 components, you know, relatively well. But then when it comes to here, we have what, like 27 different components, and those are, you know, much harder to actually get all 27 components. So things that I've done and Peishi, for example, with causal histories is really kind of lumping different components together when you get to this more highly multivariate stage.
Can I follow up on that?
Yeah.
So arguably this sort of suggests a couple of things. One is the question, do these things even exist, right? I'm not questioning that they exist, I'm saying. And then that goes on along the lines of Wui's, which I think was, if they're not significant, then we ignore them. But it also raises the interesting question in my mind that if I'm trying to build a model of the world, if these things actually do truly exist, then this is suggesting something about my tendency to want to simplify the world and ignore those things that perhaps are not the strongest components in order to be able to get an understandable representation.
Yeah, that's definitely that came up in the paper in terms of, you know, is there a really uniqueness, and, you know, could you, is it even really feasible to be thinking about information broken down in this way? And like, you know, their answer is no. You know, we you know, that we don't want to do this type of decomposition, but then what they do end up doing is extremely related, and they actually use that. They actually use that as kind of an example. Thank you. But yeah, that's it's definitely a point. Any other questions before I go to the actual kind of main thrusts of the paper? All right. Okay, so the kind of after all that background, the overall idea of the paper is a framework for causality based on the notion of certainty rather than entropy. And in a nutshell, they say that a target process has certainty that can be broken down into basically two parts. One is the certainty from itself. So you can know something about a process just by knowing or you can know something about a target just by knowing its distribution. And then there's also certainty that a target obtains from drivers, which is more like the causal network that I was just talking about. So the first focus, sorry, the first focus is on defining what this total certainty and self-certainty are. And the second focus is on this attribution of causality between different drivers. So there's kind of two sort of separate pieces going on, but they bring both pieces together to basically define causal strengths between variables. So this is their certainty and self-certainty of a target X, and the certainty and self-certainty terms are denoted by this W. And so in this framework, the total certainty is the self-certainty plus the mutual information from all the drivers to the target, which is kind of what I would, you know, what I would have essentially thought of previously is, you know, that's all the information there is. But instead of lumping in the sorry, I'm getting lunch delivered to me in stages. So instead of lumping in the target history within that I term, they separate it out. And what that self-certainty is, so that mysterious W term, is actually just a KL divergence term, which I think Uwe talked about last time we met. So in their context, the self-certainty of the driver is just the KL divergence between the distribution of that target and a reference density, which they test a few different reference densities, and that's part of the paper, is basically, you know, how much does that reference density influence what that value of self-certainty is. So they try, you know, a uniform distribution, for example, or a couple other of distribution types, and look at how that changes, because this is computable in terms of it's an information theory quantity that we can compute, and this is kind of a little bit at the mercy of this reference density. So the balance between these two changes a little bit depending on what you use as that reference density.
So I'm a little confused, Allison. So if the reference density is the true density itself, the true data generating process, then W is 0.
Well, the reference density is like a maximum entropy distribution. So the reference density is like, you assume a uniform distribution, for example. So
this is how much information is provided by knowing P in relationship to some unknown thing of I don't know anything. Okay.
Right. Yeah. Uwe.
Can you tell me the certainty measure? Is it? I would assume it's high when the certainty is high and it's low when the certainty is low, or what is the hoped for values of certainty?
You mean self-certainty or overall?
Yes, I mean, if the true distribution P of X would be a uniform distribution, just like this model, yeah, Q of X, then as Hoshin said, this term self-certainty will be 0.
Right, yeah.
So that would mean I'm maximally uncertain because I'm following a maximum entropy distribution. And that would be indicated by a 0. I'm not clear whether certainty should be high or low if you're good at predicting.
No, I think you're right, Uwe. So that's what I was confused with also. So this is Px is our guess at is what we think we know relative to when we don't know anything. So Q is when we don't know anything.
And
P
Px
is
from the data. Like, so Px is the distribution that we would derive from the process.
So when I was reading it, I haven't checked the derivation of this thing, but the way they were posing it is if Px is close to a Dirac delta function, which basically means that you are very, very certain about the value of X, then this Wx converges to 1,
Right.
so tends to 1. And if Px is close to Q of X, which is very uncertain, that log 1, the log term will go to 0. Right, so it'll be log Q over log Q log of 1, 0, and Wx goes to 0. And so that's how I was understanding this thing. I haven't worked on the derivation in the paper though. So
that makes sense. Yeah.
Yeah, that's exactly that's exactly what I interpreted from that. And they mentioned, yeah, with the Dirac delta function, they talk about, the narrower the distribution of your target, the more self-certainty you have. So, it's like if your target distribution is very narrow, that means that you have a lot of information already just from knowing that distribution. And then the other aspect of the certainty is the mutual information from other drivers. So that's the other information. So it could be greater than or less than the self-certainty.
I think what they're doing with this equation is putting a lower bound on the certainty measure, which is on the left-hand side. So basically it will not be negative. So W of X, if you are very certain about it, and then on top of it, you add anything else that is coming on from that mutual information. But if you're completely, sorry, go ahead, Hoshin.
Finish your thought. Yeah.
Yeah, no, I was saying if P of X is very uncertain, close to Q of X, then the W of X tends to 0, and then the mutual information is still positive, right? So I think they're putting a lower bound on this as compared to the joint mutual information, which Allison talked about, which can be positive or negative, which makes it hard to interpret in the interaction information. So I think they're trying to figure out a way out of that interaction information space.
That's not interaction information. That's total information. It has to be positive.
Right, right. No, I'm not saying that this is interaction information. I'm saying that the way they are framing this is to get out of this space of interaction information, working in the space of interaction information. They don't want to be working in there because it could be positive and negative. Whereas here you have a lower bound.
So I think the way of thinking of this is that your self-certainty is your prior when you don't know anything about Y, and your interaction term is the additional information you get when you know something about Y. So W of X self-certainty means that's my prior before I open the door to getting new information.
Yeah, I mean, yeah, any number of interpretations, right? So W of X is if I was just measuring one variable, and as compared to complete uncertainty, how much information I have, and then if I measure another thing, how much more do I get? I can add to it. So that's the way. Because
the definition of W of X mirrors the definition of mutual information, right? They're both from Kullback-Leibler. And so mutual information is relative to the product of the marginals. And here the Kullback-Leibler divergence is done relative to some, I don't know anything at all.
Right. Yeah, interestingly, one of the things that they choose is the Cauchy distribution for Q of X, and which was when I saw that, it was quite interesting because Cauchy is infinite variance distribution, right? So basically, but it has a finite entropy. So that I hadn't thought about, but when I looked at it, I said, okay, yeah, there's something to it which I have to work on. But then by creating this infinite variance distribution, they are essentially creating a very large uncertainty space through which they are filtering whatever you know through this KL divergence.
Right. So yes. So essentially, these are both. They write everything in the context of KL divergences. But what it turns out is that the self-certainty is the one that where this reference density assumption kind of comes in. And these two terms, what they do is they're like the importance of normalizing, and I was like, okay, so you normalize. If you divide this by this, both of these terms come out to 1, and that's what they call the causal strength. So CS is for causal strength, and essentially, you can compare the causal strength of all of the sources, so all of the kind of external drivers that are not the history or that are not the target variable itself, and then the causal strength associated with just knowing the history. So that's what the causal strength framework is. So the part of the paper is about this self-certainty aspect, and the other part is really dealing with segmenting this term up farther, because this term right now is lumping together all of the sources that you might be considering, and they segment this term out farther without using the PID, partial information decomposition framework directly. So what they end up with is a causal strength from itself, and then however many sources, there's an individual causal strength that's going to be associated with with each source. Let me go back really fast. So the thing with the reference density is that it doesn't change this term at all. So it doesn't change this term, but it changes the balance between these two terms. So it changes the fraction of information that you attribute to the target itself, changes depending on that reference density. So that's why that's important. Okay, so this is when the paper gets into all these like 1 links and 2 links and M links, and there's just a lot of different type of links going on. But the idea of all those different link types is to decompose that total information from the sources to the target into causal strengths from each source individually, and so for example, let's start with just the 2 source 1 target example. A Y to X causal link is going to consist of a 1 link plus a 2 link, and the 2 link corrects the 1 link. And I'll kind of illustrate what that means here. So for this 2 source case, we'll take the Y to X. The 1 link they define as the conditional mutual information from that source to the target, given the knowledge of the other source. So that's the 1 link. And then by definition, and same thing for the 1 link for the Z to X, it's just the other conditional mutual information term. And that kind of forces the definition of the 2 link to be this, which is what they call a correction term. And this correction term makes the 1 links plus the correction term add up to the total information. And believe me that this is also the interaction information. So this is the total information minus both of the 1 links, and the half is hanging out here because the 2 link is split between the 2 sources Y and Z. So we can't double count the 2 link. So since this is the redundancy and synergy term, it's equally attributed to both of the sources because we basically can't separate it any farther. So that's why we have the half term when we have the 2 source, 1 target. Uwe?
Sorry, I haven't read the paper. That's why I'm maybe asking a silly question. Do they discuss the needs or do they discuss data needs? How many data do you need to be able to infer or disentangle these different causal relations? Or do they work in an idealized world where you can do that from closed form distributions and you have no, say, sample size issues?
They do examples where it's all generated data. So for example, one of their examples is the Lorenz equation. And I completely forget how many data points they generate. But this case at least is really simple. Like this is just it's a 3D PDF is the maximum dimension. So it's not a super high dimensional problem yet. So these are just conditional mutual information terms. But they do go to 4 dimensions with 3 sources and 1 target. And I forget like what their data or like what their PDF estimation looks like. But yeah, I mean, they have the same concern that anyone would have with actually computing these measures. So in the end, these causal links, which are combinations of conditional and interaction information terms, they do add up to the total information. But this is kind of where I wanted to pull back to the PID interpretation. What it is essentially is that, in assuming that we don't do this, what this turns out to be is just that we take one causal strength to be the uniqueness plus half of this term, and the other causal strength is the uniqueness plus half of this causal term again. So they all add up to be the total mutual information. So it's kind of like, since we aren't partitioning it directly, we just attribute half of it to each source. So it's kind of a way of splitting the joint information and saying, well, it's joint information inherently, so it can't be separated into components. So we'll say that half goes to one source and half goes to the other source, which I thought was kind of a, like, I don't know of any other way to do it, but it is kind of an interesting assumption that you kind of separate that synergistic and redundant component to both of the sources equally.
So Allison, I mean, so the problem with all these estimations is that the number of unknowns are larger than the number of equations. So even with 2 source and 1 target, which is the easiest of all of them, you have to come up with an equation for redundancy, right? To be able to solve it. Here they are basically saying is S is equal to R. And just splitting that information across. So that's their closure model. If it was only a 2 + 1 variable problem. If they go to a 3 + 1 variable problem, they're just basically distributing the synergy and redundancies equally across, because they're not really interested in figuring out what the synergy and the redundancy, and they're just saying, okay, let's club it all together and get to it.
Right. Yeah. So maybe that they don't care, but they end up finding out things about redundancy and synergy inherently through doing all those links, right? So they're not assuming that synergy equals redundancy. They're just they know what the interaction information is, and it's this minus this, and they're just they have S plus R. Well, they don't have S plus R, but they're attributing the types of information evenly.
Yeah, that is tantamount to another equation. I mean, S is equal to R, right? I mean, or S plus, yeah.
Okay.
Yeah.
Yeah, I guess I
Go
need
ahead,
to,
sorry.
I need to convince myself of that. Because this is U plus 1/2 R plus 1/2 S, and this is U plus 1/2 R plus 1/2 S. Yeah, so for a more, so it gets more interesting when you have more dimensions, because that's when you actually come to a case where, at least from my perspective, where you can't do, or the PID is actually harder to get all those different components. So basically you have the same idea, but more M links. So you have as many M links as you have sources. So if you have 3 or N, you end up having N links, and at each level you partition evenly between that number of sources that you're concerned with. And they show this, and this does work out, so that the causal strengths add up to the total mutual information. So it's a recursive definition, where you start with the 1 links, and then from there you go to the 2 links, and that gives you, so the 1 links, the 2 links are a function of the 1 links, and the 3 links are a function of the 2 and the 1 links, and so far. And so this is just their expansion of an example of what one of those looks like. So they provide some examples, but the one where they really kind of illustrate how this works with more than 2 M links is the Lorenz equation. So they generate data using this set of equations here, and what this is showing is the self link, and the black lines and the black arrow indicates the 1 links and the self links. So the 1 links are sort of like a conditional mutual information term, or well, that they are a conditional mutual information term. And what they show with the Lorenz equation is that the 1 links and the self link is pretty small, which makes sense because there's not a lot of information that a single variable provides. Oh, sorry. We're just considering X as the target in here. So we're considering, they just pick X at first as the target to focus on. And then the previous time step, X, Y, and Z is the potential sources. So basically that is just saying that, with the Lorenz equation, knowing the history of one variable doesn't give you a ton of information about the next variable. However, we see these red lines are the 2 links. So these are sort of the pairwise sorts of links where we start to look at X and Y and X and Z and Y and Z. And these are a lot larger. And what we can interpret that as is knowing a pair of these variables actually tells us quite a bit of information, because it tells us what wing of the attractor essentially this is on. So for example, knowing both X and Y provide a good amount of information about X. And then the last thing, so since we have a 3 source, we have a 3 link. So this blue is illustrating this 3 link, and it's negative. And what this means is that, so each M link is a correction term in order such that all these links have to add up to the total mutual information. And now that I think about it, this might already be normalized. So these numbers, I think, all add up to 1. And so since these 2 links are really high, what that means essentially is that since this is negative, that means that all the pairs provide redundant information with each other. And the 3 links subtract that back out. So some of these, what I think of as pairwise synergies, are actually redundant with each other. So that's kind of, the pairs of information are redundant. So that's why this 3 link is actually negative. And then what they come out with for their causal strengths. So this is the normalized version of, let's see, X, Y, Z, and then this is I guess this, I thought this was the self-causal strength, but maybe it's like a noise term. But anyway, these are the actual kind of causal strengths that they come up with in terms of causes to X. And then they also show this with Y and Z and make some different inferences. So this is the page where I was drawing notes on what these M-links were in terms of synergy and redundancy and uniqueness in that sort of context. And it was pretty interesting because you can map any given number link to this redundancy lattice. And it kind of helps think about why some of the M-links are negative and other ones are positive, because this is a construct where you could just look at those causal strengths, which is kind of what they're going for, is like, here's, X provides 0.4 of the information. But actually, I found the M-links themselves to be more interesting because basically, for example, the Lorenz equation had a -3 link. And the only way that a 3-source system has a +3 link is if those 3 sources have a lot of pure synergy or pure redundancy, where they're actually acting really jointly or really in overlap to provide information to the target. And otherwise, it's a lot more common that you have these kind of middle regions of your redundancy synergy lattice. It's more common that the information is encoded there. So it's more common that those information components are more significant or jointly more significant than these kind of very top and very bottom, like they showed with the Lorenz equations. So there's a lot of mathematical detail going on, and I've definitely not dug into the whole thing, but some parting thoughts, and we can go back to any of these aspects. A couple of things. I'm not sure why self-certainty is the way it is, basically. So I kind of wonder why it is that like why it's that KL divergence term instead of another mutual information term where we're just considering the entire past of the target variable. And one thing that I thought of is it does simplify the dimensionality of a problem a little bit in terms of just looking at the shape of the distribution of the target and saying that that's the amount of self-certainty. And then at its core, this method, it lumps together a lot of different types of interactions that are difficult or impossible to calculate directly, especially if you have a multivariate case. And I thought that the causal strengths themselves are actually kind of, they sort of, they lump together all these lumped together terms, and it's actually more interesting to look at all the M-links because those are actually what, whether the 2 links or the 3 links or the 4 links are negative or positive is kind of what is telling you what's the dominant type of interaction going on. And yeah, so I think that's all I have. So any thoughts or questions?
I kind of like the definition of self-certainty, even though I understand it's ambiguous. But I like characterizing the information I have about a variable after I've collected some data about it relative to before I know anything about it as a kind of a benchmark. That part sort of resonated with me. And then the mutual information is adding posterior information, so it had that connection to me to Bayes' law. I'll agree. I'll just mention I'm not as familiar with the synergy and uniqueness component, so it's very hard for me to track through that part.
Yeah, I thought it definitely makes sense. Like the self-certainty term. I wonder how different it would be like if you instead chose to define self-certainty as the knowledge of the target variable that you obtain given all the historical states of that target variable, instead, because that would make that term more similar to the other term, like that would make that certainty term more similar to the I forget what they call the driver.
So you can you can distinguish between variables for which you have a past history and variables you don't have a past history. So I'm curious about the Cauchy distribution that Praveen mentioned, because here we're dealing with everything in continuous spaces, but if you push this back into the discrete space, then the uniform distribution as a benchmark, there's no problem, because you're basically saying, what are the total possible number of states my system can take on, and there's no ambiguity in terms of what's the minimum, what's the maximum entropy distribution in that case. It's only when we go into the continuous space that we end up with this sort of problem.
Yeah, also, I mean, in the continuous space, the distribution with the maximum entropy is the normal distribution, right? They depart from that and use the Cauchy, basically making it even. I mean, there is no, basically in the real sense of interpretation, its uncertainty is unbounded. It's infinite variance distribution.
Sorry for my ignorance, but can you remind us what a Cauchy distribution is or looks like?
So it's shaped pretty much like a normal distribution. So basically normal distribution is closed under addition, right? So if you start with a normal distribution and you sum normal distributions, you get normal distribution. If you start with any other distribution, you end up with a normal distribution. That's the central limit theorem. Mm-hmm. There is a generalization of the central limit theorem, which ends up with something called a stable distribution. So there are other families of distribution which are closed under summation in there, and those are called stable distribution. And they have a parameter which ranges from 0 to 2, 2 being the normal distribution. And everything less than 2 is pretty much an infinite variance distribution. Between 1 and 2, you get a finite mean, and less than 1, you get an infinite mean and infinite variance distribution. They're still closed in there under summation. So it's a very, very interesting set of distributions. Cauchy is that other boundary between finite mean and infinite mean. So that's the parameter alpha, I'll call alpha at 1. So Cauchy happens to be infinite variance, finite mean. Is very much shaped like a normal distribution, but it basically is much longer tail. So anything, so if you think about convergence of these with alpha is equal to 2, everything will converge or greater than 2. But you've seen these plots where alpha, PDF tail plots, and then the alpha, whenever it's less than 2, it doesn't converge. Those are long tail distributions in there. So Cauchy ends up being in that family.
So by convergence to the mean, you mean that if I keep adding random numbers, it'll never converge to a fixed number.
Exactly. So, I mean, this is the usual fractional distributions, right? So the idea is that if you take these distributions and you generate 1,000 values and you compute the mean and the variance, and then you can compute 10,000 values and 100,000 values, these mean and variance will converge, right, to some value. But when you have these distributions, essentially once in a while, such a large number will pop up that it will throw out the estimate of the mean and the variance. And then you start converging and suddenly a big number will pop up in there. And this number basically skews your denominator, which is n, right? So
this is sort of interesting, but that's sort of interesting in the earth science context, because we always have our data sets are always data sets where we can't be sure that it's actually converging to a mean, right? But I'd never heard this concept before, so that's cool.
Yeah, no, so this was all in my PhD thesis when I was working a long time ago. We were basically looking at fluctuations of rainfall, and you end up with very large fluctuations, and then your distribution doesn't converge in there. The interesting thing about stable distribution is you can get non-symmetric stable distributions, right? So it doesn't have to be symmetric like normal distribution. So it's a very interesting world. And so when I saw that Cauchy, basically seemed interesting. What they were trying to get to is basically something which is untractable but manageable still. They could have chosen normal distribution and say that's my thing and I'll work with that. They probably would have ended up with the same interpretation.
But sorry to push this a little bit more, but when you gave that example, then it made me think of suddenly a data point with a very large surprise, right?
Yeah, that's what it is. I mean, yeah. So you look at the Hertz phenomena and all that, right? I mean, everything is just, yeah, once in a while you'll get this. So we are used to, so when I used to teach stochastic hydrology, whenever you're talking about random walk, you basically are just looking at very small fluctuations and going through that. To think about this, you have to essentially think about, so basically the random walk example is a drunken man walking on the street, right? I mean, you fall around. Here you have to think about a drunken Superman. So this guy can jump from one end to the other and then
does this imply that we should actually be using distributions like this to account for the black swan effect?
Yeah, Black swan effect goes into that space. I mean, that's the whole concept is developed out of stable distributions.
Cool.
Yeah, sorry for the digression here.
No, I didn't not really go into the reference distributions. The one thing that I did notice about so that they compared a few reference distributions, so uniform, Cauchy, something else, maybe as a normal distribution, it didn't change any of their answers that much. So the reference density had an implication. It just wasn't that large of an implication. And I think probably because of what they were looking at was that the driving sources did provide a lot of information, and that would kind of have a tendency to be the larger component, that it would become more important if you had a process that had no drivers, or that if you were just looking at that self-certainty term by itself.
Yeah, I mean, sorry, go ahead, Hoshin.
Oh, I don't want to dominate this. I mean, this is all kinds of interesting thoughts. For example, my next question to you was going to be, do we know anything about the return period for these extreme events? Because now you get into this interesting situation as to, how long do you have to wait in order to get one of these black swan events? And, is there some distributions associated with that and so on?
So yes, so basically, I'm trying to remember, the tail of the distribution behaves as a hyperbolic distribution. So probability of capital X greater than X is essentially proportional to X to the power minus alpha, where alpha is this number between 0 and 2 in there. So the summation of these values as well as the tails of these values, and not summation, the tails and the maximum, they have the same distribution. Basically, the whole statistics is dominated by a few extreme values.
Thanks, guys. Apologies, I have to go, but
yeah,
that was very interesting. Thanks, Allison. Really appreciate it.
So next week, are we doing, Uwe, are we doing with the other paper?
Not next week, but next time. I think Stephen
Next
will
time, yeah.
present the paper by now.
Yes, it will be on May 19.
Yes. We'll remind Stephen of it because he may tend to
Yes, I communicate
forget
with
that he will
him
present.
today. Yes. Mhm.
Bye.
Okay, thank you, everyone. Thank you, Allison, for the great session.
Thank you. Bye.
Yeah, thanks for
Bye.
digesting it so well.
Bye.
Bye.